Okay, so today I'm going to talk about the topology, especially. So here we will learn homology and cohomology, and also fundamental group. If time permits, the homotopy group. Okay. So we will learn here algebraic topology. We don't care about manifold differential and so on. And in particular, we no longer talk about how to say. But sometimes we talk about some space that is not manifold. So that is not manifold, but it's topological space. We only talk about homology. And the notion of homology, I mean, everything is talking about homotopy invariance. In homotopy invariance, roughly speaking, you can just do the continuity deformation space. For instance, this Rn mod point origin is homotopy equivalent to Sn-1 sphere by contracting the space x goes to x divided by outside body. So that's the actually it will give you homotopy between Rn mod point with Sn-1, and one can introduce some notion about topological invariance or homotopy. The notion of some invariant after homotopy. So all the notion is given by the first idea is given by 1895. I already the series of paper on card, which is available on the internet. So maybe it's worth looking at. It's a very important notion in physics. So that's what we are going to see. Okay. So from here we can talk about error characteristics. Is introduced by something like some space. I call it in here I no longer talk about manifold, so I think I'm talking about some K such as sum of -1 to some alternative sum of the dimension of homology, something like this. Here to definition. So that's the so homology fundamental all topological that actually encode the information topology of manifold. Okay, so and then at the end of the day, this cohomology is related to, even though we don't introduce anything differential structure as a vector space it's related to dynamical homology. Cohomology we talk about. So here we definitely use differential form and so on. But from here, now, I think 2 or 3 lectures, so I'm not going to consider any differential structure and so on. Sometimes space can be non-manifold. Okay, so so I'm going to talk about the basic notion is so we kind of approximate the manifold by so-called complex. The complex. So I'm going to introduce. I think usually if you go to mathematics department, people use singular complex, but bit more complicated. So I'm going to talk about the simplicial. It's very simplicial complex. It's this what is it called? It's a bit. Oh my goodness, my English is getting worse. So let's first define a simplex. So the definition Q simplex is the complex form of. So let's consider general position. So A0, AQ in Rm. So this is the linearly independent. Linearly independent such that the sigma is the set of the space inside Rm such that the sum of Ti and the Ai where the sum of Ti is equal to 1 and the Ti is equal to 0. For instance, if you take that means that if you take ABC, A0, A1, A2 inside R3, so this simplex is nothing but again to nomenclature. I don't know what happened. What's going on? So this orange one is sigma simplex. This is a Q simplex. It's a two simplex. Yeah. 2 means 2-dimensional. Okay. So here it's Ti just parameterize a point inside of this orange, and if you set one of the Ti to be 0, it becomes edges. Okay. And if you set the 2 Ti to be 0, it becomes point. So and at 0, so these are called vertex. These are called vertex. Vertex, and sometimes it's called this span. A0 to AQ span, this simplex sigma. Yeah, and this Ti, this T0, TQ are called barycentric coordinate. Yeah. Okay, so yeah, so the bunch of, in particular, so the boundary of sigma can be constructed by setting sum of Ti equal to 0. Okay. Sum of Ti. So if you set sum of Ti to 0, it becomes boundary. It consists boundary, and so complement of the boundary is called the interior. So this is boundary and the interior of the simplex, and you just put the sum dot Okay. Yep, and then as you can easily see, for instance, so there's a face, some face is spanned by some subset of these vertices. So for instance, A0 to AQ minus 1, Q minus 1 is also some Q minus 1 simplex that is included into the Q simplex, and that is called face. It's very simple notation, and if you it's called oxymoron, simplicial complex. Okay, it's an opposite word. I think it's not simple and complex are different. The opposite word. In Japanese. Anyway. Then, so we will introduce some so-called simplicial complex. The complex is just made of just simplex. Yeah, a bunch of simplex. So simplicial complex. Oh, thank you very much. But I think I already gave up this to the link. We'll open that. Anyway, so thank you very much. Simplicial complex is a finite. So this is the finite set of simplicial K of simplices. Simplices is the plural of simplex. Plural simplex, and then such that it satisfies the following condition. Given so this finite set K of simplex, if the sigma and the tau is a phase, so this is the phase. It's called let's go tau, and then sometimes people face. This is face, and the people write face of yeah. This is people write like this way. So, and if tau is a face of sigma, so this is simplex face, then this is also included inside of finite set K. And also, it's very trivial. It's very trivial in K, and then sigma and tau. Is either empty or face of both sigma and tau. It's very simple. For instance, I just draw so this is the example simplex. This is 0 simplex, and the 1 simplex, and 2 simplexes here, and the 3 simplex is something like a tetrahedron. Okay. By the way, sorry about the homework this week. I made a huge horrible mistake about this second one. The cost. Yeah. So, and then so you can just combine finite set of the simplex. So for instance, this is 2 simplex. You can just have whatever, like this way. These are called simplicial complexes. It becomes a bit more complex. That's why I think people call it this is simplicial complex. But this is not. So for instance, this is not. Okay, this is not simplicial complex. Can you see the reason why this is not the simplicial complex? So for instance, if you look at here, okay? If you look at here, this is not face of this two simplex. Okay? Do you understand? It's not the face of two simplex. So therefore, this is not the simplicial complex. Once you have some definition and so on, just consider some example and counter example and so on. Okay, so yep. So for instance, if you look at this one, clearly this is not the subspace. So this is not. If you only consider the space of space of, for instance, you can also consider disjoint union. Space that is considered so space of this simplicial complex, it is not the subspace of Rn. So therefore, so we just consider, if you consider given K is a simplicial complex, and then if you write down the absolute value, it's look like absolute value. This is just a union of the union of simplices in K. And then unions. And for instance, so people just write K of D is called a bunch of D simplex in the union, and this is called D skeleton. So the skeleton, and for instance, in this, if you consider this as the K, KD is something like that. KD is this one. Sorry, K3. So this is K3. 3 skeleton. There are two skeleton. For instance, this one is one of the one, and this one is 2 skeleton, and also this one is 2 skeleton, and so on. So there's a K2 and so on. So very simple so far, and then so given a manifold or space, so given the topological space, given the manifold, or more generally space, topological space, generally. Topological space, given a manifold n, you can just consider homomorphism H K to n. Homomorphism. If you have a homomorphism is that it's like a topological analog of diffeomorphism. So homomorphism is that there is an inverse, H inverse, such that h dot h inverse and is identity, and the h inverse dot h is identity. So in this sense, it's just m goes to m. This is k goes to, and it preserves topology. The map is preserve topology. Topology means like you can open set is mapped to open set and so on. So yeah, homomorphism one-to-one map. That one-to-one map that preserves some topology. Okay, so let's consider. So for instance, if you consider the boundary of this one, so boundary of this guy. So boundary of this guy is if you consider boundary of this one, it's a finite set of one simplex. Okay, one simplex. So that's also simplicial complex. That is the and you can take homomorphism as S1. Okay? So I don't care about the differential structure. So even though there is some like a vertex that is not at this point nothing differential look like, I don't care. It's just one-to-one map, okay, to S1. So if you look at the boundary of this orange, it's topological S1, and you're going to construct. So one can construct homomorphism, and this is called a simplicial one sphere. In general, so if you have n simplex, this is n simplex, and boundary of sigma is, you can just consider Sn minus 1. You can construct the homomorphism, and this is called triangulation. Once the ring, the bell rings next time, can you steal the color chalk from next room? Can some of you guys steal color chalk? Only tiny pieces. Okay. So good. So what I'm talking about. So this is called a triangulation. So the reason why, so this triangulation is not unique. And for instance, if you consider S2 can be triangulated like this way. So this is two simplex. No, not two simplex, three simplex. And then, but you can just combine. Thank you very much. Two simplex combine together and get rid of the middle plane here, and you just consider the bound. How to say? So you just consider three simplex and then get rid of interior. Okay, you get rid of interior. Then you get the another triangle S2. Okay, understand what I meant? So I no longer consider interior of this how to say two. So you just combine two tetrahedron. Okay, and then forget about the inside. Then this is another triangulation of S2. Okay, so the nice thing about this triangulation, this is not nice thing, sorry. So this is another triangulation. The other triangulation is more something like let me try to draw nicely. one can triangulate S2. So S2 can be literally it's triangle. Okay. So each face has a triangle. So that's why it's called triangulation. So S2 admits another triangulation, but this can be used for triangulation. Thank you very much. Good. If you identify the opposite simplex or simplices, you can identify the opposite simplex. So you can if you identify opposite, identify opposite simplices, then this gives the triangulation of RP2. RP2. Okay. So I'll just give you a bit of intuition on RP2. Where was the? It's called, I think, analytics cetus. The Pankers, the paper. It's a very famous paper. Cetus analysis. Yeah, cetus analysis. I think originally it's written in French, I guess. So if you identify faces, I think what you end up with something like yeah. I'm not good at drawing, sorry. Something like this one. And then as a set, this part is identified with this part, and also so this part is identified. This part. Okay. As I said, identify the opposite edges are identified. And the rest of the part distinct point. Okay. So therefore, and this yellow, and this point is identified this point. Okay. So therefore, this becomes just essentially a circle. Okay. And then RP1 is S1, right? Okay. So therefore, if you look at this, so RP, so essentially RP2 can be understood as R2. So if you get rid of these yellow edges, essentially it's the same topological same as R2. It's just an open disk. So if you look at northern hemisphere. So therefore this is RP1. Okay. It's roughly speaking, if you look, sits on the R2 plane, and at the infinity, RP1 is living. So you can consider RP. And similarly, RPN is also has the same structure. RPN is union of RPN minus 1. If you look at the Euclidean space, at the boundary, the smaller projection space is living. And you can do the iterative way. So Rn at Rn minus 1, and then Rn minus 2, and so on. Okay. So RPN can be constructed by the iterative way, just union of Rn. But Thank you very much. Thank you very much. And you can just iterate. So you have to be a bit careful about the infinity. But that's the structure of our projection space. Yep. So, okay. Since manifold M, so if you consider triangulation manifold, this is manifold can have orientation, the notion of orientation. This has a notion of orientability and so on. Orientation. So therefore, one can just introduce the notion of the orientation in the simplex too. For instance, in this example, so yeah, for instance, so one can just put the orientation on this simplex so that the if you permute the vertices, if you permute vertices, this A0 to A Q, so this order set, you just consider order set, and then if you permute, let's see. So you can consider this the order set, and this has opposite orientation as A1, A0, A2, A3, AQ. So this has opposite orientation. So once you permute two vertices, okay. So I just swap A0 and A1. Okay, you just consider all the vertices, and you just if you permute two of the vertices, it becomes opposite orientation. And more generally, if you consider the permutation by whatever, more generally, pi is the element of SQ plus 1. S is a permutation group, and pi, order of pi is the even, its orientation preserving. If it is odd, it's opposite orientation. So that's what I mean. Okay. So you can just introduce the, consider the order set, and then orientation can be considered. Even if okay, I think there's a typo in the lecture note. Yeah, it should be Q plus 1, and then this is not sphere, so I should change the notation. Okay. And then, so we consider so-called chain group. So it's a group. And the meaning of chain will be apparent later. So the group is given a simple complex chain group CQ. Okay. So K is the simple shell complex. And then so inside of here, K Q is bound by the order sigma 1, sigma L. So everything, so they are all Q simplex. simplices. For instance, in this example, so this is the differential complex, and then K2 is bound by this 1, 2, 3, 4. Okay, so there are 4 faces. Okay, so sigma 1, sigma 2, there are 4 two simplices. And then we just consider as the abelian group as the free abelian group as CQK as just a bunch of copy of sigma 1 C sigma Q. Oh, not QL, sorry. Sigma L. Okay. So you just consider a bunch of copy of Z. Okay. So essentially, so this is isomorphic Z plus. I'm just repeating the same thing. L copy of Z by just zero sum. I mean Z. So Z is an integer, so it's a group. Okay. It's more. It's a group, and then moreover, it's a ring. But anyway. But we just only consider some group, and this here we just consider a abelian group as a abelian group. So do you understand the notion of abelian? So it's commute, okay, by group operation. So essentially A plus B is equal to B plus A. Okay? A and B are integer. Okay? A and B are integer. So this means that the chain group, you just count the bunch of copy of simplex. Okay? Bunch of simplex. Very simple notation. And then okay, so then so we define so boundary homomorphism in such a way that the so given the simplex sigma, which is spanned by Q plus 1 vertex, okay, given the sigma, then it's mapped to the bunch of copy sum of I equal to 0 to Q, such that it's an alternative sum of Q simplex A0 AI AQ. So hard means you omit this vertex. So let's see. So for instance, if you start with simplex, two simplex A0, A1, A2, and you just also consider interior, okay? Interior. This is two simplex. Is mapped to essentially, let's do honestly. The first one is let's pick I as a 0. Therefore, so this one A1, A2, okay? And minus next is A1, A0, A2 plus that's the operation. Do you understand? Do you understand? So I hope you understand what it means. So these are one simplex. So one simplex with sign, okay? With sign. So this is called boundary homomorphism, boundary map, or boundary map, or as a group. So these are groups. So therefore, it gives homomorphism. As a group, for the between group. So homomorphism, so you can just, how to say, consider two copy, if you consider two copy of, so it's a group, and you just count the integer number of simplices. If you consider two copy of these two simplex, or let's almost three copy, you just multiply 3 and 3 and 3, okay? Here's, okay. That's the meaning of homomorphism. You can just, if you add the simplex here, at the end of the day, here is also you need to add it. So that's the meaning of homomorphism. Okay. I think a bunch of notation is a bit. And one can show that so this is just very similar to a drum differential, right? The serial derivative we consider. Do you remember? So d omega, it's opposite. It's almost like opposite. N goes to, for n, it goes to omega n plus 1. N plus 1 of omega. So this is the exterior derivative of Baudrin homology. But here you just decrease the dimension, essential dimension. Here you increase the dimension. So therefore, we are going to talk about homology. And here it's called homology. Drum called homology. Okay? That's a, so therefore, and then here we had a relation d squared is equal to 0. We can have also the same relation q dot. So there's a typo, lots of typo in the lecture note. So this is, one can show. I'm not going to do that. Shall we do the example? Oh, let's do an example. So we are physicists. So let's do the example. So here we take boundary map 2. So next, we map 1. Okay. So this means the here we just consider a1 minus this is plus a1 but minus a2. Okay. And then here you have to take okay, and plus a2, and then you have to sorry. It's a bit confusing. I have to take it correctly. Yeah, so first I need to take, what am I doing here? I think I'm doing something stupid. Yeah, I have to do cyclic. So first, if you apply boundary map on this one simplex, you just first get rid of this one. And what's left is this one, right? And you get plus here, and then next you just get rid of a2, so you get the minus of a1. Minus a1. Next, so you need to do this cyclically. So you have to first get rid of. First, you need to get rid of this guy. Okay? Huh? this should be yeah.
When you get rid of A1, theorem should be minus A2.
So this should be the case. Am I correct? Yeah, I think I'm correct. So yeah, first you need to get rid of this one. Next, okay. So then plus sign A2 and minus sign A1, okay, A0, okay. And the overall minus sign here. And next, you first get rid of this A0, and you get the plus A1, and then next you get rid of A1, you get the minus A0, and the overall plus sign. If you sum them up, you get 0. Okay? Okay, so let's move on. Okay, so then you can have chain complex and you just apply boundary mark. It's the same as drum curve homology. So in drum curve homology, we just start with 0. You just start with the omega 1 and you just apply exterior derivative. That's what we did for, upper script. So it's opposite of drum curve homology. So you have a differential forms. That's what we did for the end form or K form here. So this is called chain complex. Complex. Yeah. Complex. So it looked like a chain. Okay. It looked like a chain. That's why it goes to a chain group. With a chain group, and this is a chain complex. Okay, and then similarly we can define the homology of K of Z coefficient, which is the kernel of phi and the image of phi K. So again, we have that so it's a vector space or like a abelian group. It's a abelian group. So again, we just look at the boundary map will be like this way. Okay. Why am I doing such a stupid? So then this is a boundary map, and then our thing is here, and then so we again have something like the boundary map, but the sum of them is mapped to just a 0. Okay. So this is the kernel. This yellow one is this one, this guy, and then this red guy is this guy. Okay. Okay. And the homology is the difference in between. Okay. So this is this guy. Okay. So this is called Q's homology. Okay. And in particular, I think it's better to make a notion. So this is called cycle. This is called Q cycle. And sometimes people just write down Q, CK, and red is called Q boundary. And then BQ. Okay, so that's the notation one can consider. So given a manifold M through triangulation, this is not unique, okay? So from here, so this is triangulation. From here, one can consider chain complex. Chain complex, essentially this runs for Q0 to N. Okay, such that N is a dimension of manifold. So M is a manifold. Okay. This is chain complex. So this depends on, so this chain group, it depends on triangulation. However, and also one can just consider a bunch of homology groups of K and Z coefficient. It's very important to keep this Z coefficient. Okay? So sometimes one can just consider, we can do the same operation. So if you consider instead of Z coefficient, you can replace by R coefficient. Okay? For instance, R coefficient, everything. And everything you just consider the R copy. Okay? So R means you can just have fraction. The R is also a abelian group. That's a abelian group. It's a more of a ring. Overall field. Anyway, so then you can do the same operation, but then now if you do the same, this was replaced by this will be replaced by HQ, K, and R. So R coefficient, it becomes R coefficient. And then there is a huge difference between homology group of R with coefficient R and the coefficient Z. And homo, you will see that. So this is homology group Q0 and N. And we will prove that this is independent. Of triangulation. Triangulation. Okay. So this is the essence of this is the essence of the homology group. Homology, if you consider chain group, it depends on the triangulation. However, once you take the difference between cycle and boundary, this becomes independent of the triangulation. So therefore, this has the information of manifold. So therefore, this can be replaced by k by n. So independent means that given a two triangulation, different triangulation. So homology group of K Z is isomorphic to other group. Okay. So that's what I mean. So therefore, you can just replace K by N. Manifold. It encodes information. They encode the information of a manifold, not the triangulation. For instance, let's consider S1. With two triangulation, this way, okay? With two triangulation, okay? And as we already see here, once you consider all the one simplices, and you sum them up, so A0, A1, A2, okay? And then if you take the boundary, so let's take homology. Oh my goodness, I already. Okay, let's do step by step. So that one is next one. Okay, so let's do step by step. So let's consider this case first. Let's consider this case. So then K is spanned by 0, 1, 2, 0, 1, 2, 3. These were the differential complex. And then C0K is spanned by let's do the step by step. So it's 2, and then oh, sorry. So, okay, so those are chain group of this integer complex, and clearly it's immediately see that we already did the exercise here. Therefore, what you can easily imagine. So what you can easily imagine that the so if you just consider C1K and C0K. Okay. So this chain complex and it's a boundary map. And then we already did exercise over there. So if you consider the map, just consider element which is A0, A1 plus A1, A2 plus A2, A0, on the boundary map, under the boundary map, this becomes 0, okay? This we already see that. Therefore, this is inside. So therefore, this is inside. This element is one cycle, okay? So therefore, inside Z1K. Okay. However, there is no image. There is no image from 0 to here. Therefore, this is indeed the element, the homological element of K or S1. So as you can easily see, this one is essentially, so if we just approximate this one is circle, right? Circle with orientation. A0, A1, A2. Like this way. Okay? Therefore, if you add them up, it becomes entire circle. Okay? And then clearly, boundary means really take the boundary. There is no boundary on circle. Okay? So therefore, it becomes 0. That's what it means. Okay? So therefore, this is the element first homology group. And what is zeroth homology? So what is zeroth? H0 of S1 Z. What is this one? So any element A0, A1, A2, once you apply the boundary map, you get 0. Everything goes to 0. Okay? However, so they're all elements in 0 cycle. However, one has to be careful about the image of this boundary map. You have to get rid of the cube boundary. And we already know that the boundary of A0, A1 is equal to A0 minus A1. Okay? So therefore, this is the image. Okay. So therefore, so this will give you A0 is equivalent to A1 inside the zeroth homology. Inside. So they're the same element. So Z1 and Z0 is spanned by A0, A1, A2. Okay. The boundary map, a boundary is A0 minus A1. And then A1 minus A2. And then unfortunately I don't have a space. So let me write down here. So, and then A2 and minus A0. So it's spanned by this element. Okay? So therefore, so here is a group. It's a group. So it's a group, so if you have A0 minus A1, okay? So this becomes 0 inside, this becomes 0 inside the zeroth homology group. You understand what I mean? So this means that this is really the quotient. Once you have the boundary of the one simplex A0 minus A1, you ignore. Okay? That's what it means. So you can ignore So inside a homology group, but you have to impose these elements are trivial element. That's the meaning of quotient. So therefore, inside A0, everything A0 and A1 and also A2 are all equivalent. Okay, it's the same equivalent class. So therefore, everything is the same in S1Z. The same element due to this condition. Okay? So therefore, this one is all as isomorphic as a group Z. So Z0 is isomorphic to as a group what? Z0 is isomorphic to what? How about B0? Huh? Good. If you impose two conditions, this implies the third condition. Okay? So therefore quotient, so H0 is the quotient of C0 divided by B0, so therefore this is isomorphic to T. Okay? That's another way. So therefore H cubed, the people write like this way, is Z cube equal to 0, 1 and 0 otherwise. People just write down like this way. We got it. And from this analysis, it's easy to see that the so then what's this? D2 is just disk. I mean, you have to specify Q. So we know that so we can just take the differential triangulation, triangulation, okay? We know that this one, what do you say? So one skeleton, I mean, so it's called the one differential complex is 0. Okay, first of all, okay, what is the, okay, let's do step by step. What is Q2? Q equals 2. Q equals 2, what? Okay, maybe let's start with Q greater than 2. What's Q greater than 2? 0, okay? Issue is 0. There is no higher dimensional simplex. So what is Q equal to? How do you see that? Z2 is 0. How do you see that? The boundary of this triangle, okay, inside is the boundary, right? So it's non-zero. So therefore it's non-zero. What is q equal to 1? Q equal to 1. Q equal to 1 situation is similar to upstairs. We know that this one is, what was it? This one is one cycle, okay? One cycle, but it's a boundary of two cycles. Okay, do you understand? So therefore, it's trivial element as a homology. Do you understand? So, since this circle is bounded by disk, okay? The boundary of disk is circle. So it's already disk is mapped to circle, this red one. It's included this red one. The one cycle over there is included this red one. Okay? So therefore, it's no longer non-trivial, okay? It's a trivial element in homology. And what's the q equal to 0? Q equal to 0. What's this? 0? Why?
Because it's just v plus v plus v over v plus v. It's just
Good. So if you look at the zeroth element argument, exactly the same as upstairs. So therefore it should be Z. Do you know what it's called? And once you replace n, then 2, so therefore this is equal to 0 when, so Z equal to 0, 0 otherwise. Okay? So therefore, homology group of disk is different from homology group of S1. Okay? Here, non-trivial element in first homology group. Okay? But there, no. So they are topological different. Okay? That's the power of homology group. Since we can just visualize like a one-dimensional manifold or two-dimensional disk, but if you go to higher dimension, this is very powerful tool to understand the topology of the manifold, higher dimensional manifold. And even if you replace n, so forget about this one. Oh yeah, it's okay. It's okay, sorry. This also holds. Okay? You can easily imagine. It's the same argument. And what is it called? You already knew. It's called Poincare lemma. This is called Poincare lemma. So the reason why the homology group is so simple for this is this can be shrunk to the point. Any disk, so there's disk n is a point mapped to x goes to tx continuously move to the point. So which means that so these maybe it's better to draw the picture. So you can just continuously move to the point. any point on disk, it just shrink to the point. That's called contractible. On the other hand, the circle, if you consider circle, there is no interior, right? Interior. So therefore, you cannot shrink to the point. So that's the difference. The Poincare lemma appears in Drunker homology. Do you remember? Poincare lemma of Drunker homology. Okay, so that's the Poincare lemma of Drunker homology, as you remember. Okay. Any questions so far? Okay, I think it's a good time to take a break, I guess. Let's take a 10 minutes break. So if you have a question, so the homework, if you don't submit it today, it's okay. Deadline on Sunday night. You can just please submit a PDF file on Sunday night to the e-learning. And I'm so sorry, I forgot to bring the Escher's book today. I think I'm too occupied and I forget many things. And if you have a question, just tell me. About homework, whatever. Did you grade homework? Okay. Yeah, solution 4 will be posted tonight or something. I need to edit a little bit.
只有一个二维子的，就是那个边，二维子，那就是它的边界，所以怎么样？就是它只有一个二维子，你去扫要。所以它倒回它的原则是那个边，它就是它一直把它做成它。
Boundary of this triangle is boundary of this is just it's not zero. And therefore, it's not the element of homology. It's not cycle. Two cycles. This is Q in one case we only know that the only this guy is one cycle. Yeah. But it's an image of two boundary of two cycles. Two simplex. Therefore, it becomes trivial. So, yeah, Z1 is equal to Z1. Yeah, so therefore, homology is trivial. The one cycle, it's a one cycle, but that's inside a boundary. Difference, one cycle. I mean, if you apply boundaries, the boundary is not So it has to be some some whatever element, what do you call sigma has to be zero in order to be homology, element of homology. Oh, sorry, I shouldn't erase here. So would it be better to keep this deadline to Sunday night? Like every Sunday night. That can be done also. Instead of just setting Tuesday morning. Do you prefer that one? From next time every time Sunday night. That can be done. Do you prefer that one? Okay. I see. Now I saw. Okay, shall we start? So, how many of you want to keep the deadline to the Tuesday morning? How many of you want to keep the deadline to Sunday night? Okay, one more. 1, 2. So Sunday night. Just raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, how about the bring original Thursday morning? 1, 2, 3, 4, 5. Okay, then let's move it to Sunday from now. If you want, you can submit this Tuesday. Okay, so the bring Tuesday, that's fine. But you can submit whatever method. But please, if you want to submit e-learning, please submit in PDF and then readable way. Do the app in iPad to do the scan. So if you have the iPad, you can download the app to scan the homework to the PDF. Okay. So you can use that. Okay. So we will move it to the listening Tuesday. Yeah, I didn't post this homework yet. Yeah, but I will post today. But anyway, so most of you guys are still doing homework 5. So let's. Oh yeah. So we talk about this. This is independent of triangulation. So we can do the same exercise. Same exercise for a sphere, S1. If you consider, so we already did this case, and then you can do different triangulation, A0, A1, A2, A3. Okay. So this is different triangulations S1. Okay. So what is the one cycle? One cycle is very simple. A0, A1 plus A1, A2 plus A2, A3, A3, A0. Okay? This is one cycle, right? I mean, it's just one cycle. There are no boundaries if you add them up. Okay? Okay. And then, so therefore, this is the only element, okay, in one cycle. And again, if you do the same procedure, what you end up with B0 here becomes just the plus Z and plus Z. Okay? Do you understand? So you have a full copy of vertex, but four edges, but this edge is equal to this edge. By taking differential, non-differential boundary. So this edge is equivalent to these edges in once you take the if you add them up. So therefore, at the end of the day, H1 of S1 becomes Z. What did I write? This. So it's independent. You can easily see independent triangulation. Okay. So we already know that the manifold we just considered a smooth map. We want to see is a similar thing. So you have a triangulation, another triangulation for n. The question is, can you map? The question is, can you construct a map between K, this is for simplex map. Is a map that assign the vertex. So let's consider K0 is spanned by, let's consider A0, AL. Then K1. I'm sorry, I told you wrong. Sorry. So given so this is if A0, AL is simplex, in K, then F A0 AL is also what I'm saying is correct. Is also simplex. Yes, it's simplex. in K prime. So for instance, yeah, I think so. The A1, A3, A2, A4. So this is K. Let's go. This is K. And then another simplex is the K prime. So and then the map F subset F A2 F A1. So this two simplex collapse in this one simplex. Okay. So this A1, A3 are shrink to the point. Okay. So A1 is shrink to the point, and the two simplex collapse to the one simplex here. However, if you identify, if you map A3, so there can be a map. You can consider a map. A3 is mapped to here. Then this entire two simplex is mapped to these two simplices. Okay. This one and this one. It's no longer simplex. You need to consider two simplex, two simplices. You understand? This guy and this guy. So somehow one can construct. You just collapse. You can identify this edge, and collapse this one into the origin to construct this map. But then, so this simplex is mapped to two simplices. Therefore, this is not simplicial map. Okay. But anyway, so it's a very simple operation. So just simplex is should be mapped to simplex. So given a simplicial map, this induced homomorphism in the chain group is a homomorphism in such a way that the so in homomorphism, so the essentially you just map A0, AQ to F A0, F AQ if AI is not AJ. Otherwise 0. What does it mean? So if F keeps the dimension of the simplex, it's okay. Just keep it as it is. Otherwise, you just get 0. That's what you mean. So let's look at the example of upstairs. So this one is simplicial map. So this is simplicial map F3. Okay, this is simplicial map. So this two simplex is mapped to this one. Okay. So therefore, so as a homomorphism of the chain between chain group, this yellow is mapped to this yellow simplex is mapped to 0. Okay? Oh my goodness. You should correct me. Okay. So for instance, A and A1 and A3 is mapped to the same point. Okay? Same point. So therefore, 2 simplex collapse to 1 simplex. So therefore, it used to be the element of 2 chain group, second chain group, but it's mapped to somehow the element of first. But there's no corresponding element in the second chain group in the image K prime under this map. Okay? Therefore, it collapses to 0. Okay? On the other hand, if you consider 1 simplex here is identically mapped to here. Okay? So they are distinct point. They are mapped to. So therefore, A2, A4, if you consider Q here, Q is equal to 1. Upstairs, A2, A4 is mapped to just FA2 and FA4. Okay. So that's what's going to happen. So if you consider this edge, 1 simplex is mapped to this simplex, so therefore it's non-trivial map, induced non-trivial map. On the other hand, there is 1 simplex here, okay? It collapses to the point here. Therefore, it goes to trivial 1, okay? That way. So that's induced homomorphism in the chain group. I mean, as a physicist, I mean, it sounds a bit intimidating, but we are doing very simple operation. Okay, so they're given the chain complex K and the K prime. So K prime, and there is a simplicial map. And then here, one can just consider chain group, whatever, let's go n, maybe, Cn minus 1k, and so on, chain complex. I'm going to erase it because I don't have space to write down. Okay, and 0. And you just consider the boundary map, just compose boundary map. Okay. So boundary map, but F will induce the homomorphism between chain group. Okay. So then, okay. So then the question is, given the element here, simplex here, you can just bring boundary map and homomorphism here. But there's another route. First take homomorphism and take boundary map. You can do the both. And it turns out that this is compatible. So this means this one, this way, and this way is the same, which means that the boundary map F star is equal to F star and the boundary map. We can easily show this is the case. I mean, by using property, I have already erased. So let's write down the property here. A0, AQ is mapped to FA0, FAQ if FAI is not equal to FAJ for any I and J, distinct I and J, otherwise 0. Otherwise. Okay. So therefore, take boundary map. Okay, take boundary map, right? First, let's take boundary map. And what you end up with, the one I already erased, something like a bound sum of -1 I. What is this? A0 equal to A1 check AI equal to AQ. That's what we get. And then you get map by F to the okay, it's better to write down properly. So therefore, so let's do this step by step. So this way and this way, let's look at you get the same thing. So let's start with A0 equal to AQ, and the boundary map will reduce minus to the I, A0, AI, AQ, and then this will induce F star will induce -1 to the I, FA1, FT0, dot FAI, FAQ. Okay, that's the, once you do the first statement, you get F0, FAQ. Okay, so if F0 not FAI, FAJ, for any distinct I and J, then it's clearly the map boundary will bring you to this one, right? That's we already learned. So given us Q distinct point, take a boundary, you just omit one of the edge and then take alternative sum. Therefore, you can easily see this way and this way is the same. So that's what we mean here. Okay? That's what we mean here. So therefore, you understand? You understand what I mean? And also, let me think. That one is a bit more thorough. So this means, let's just step by step. So this means that the ZQ sigma is, ZQ means once you take the boundary of sigma, which is 0, okay? Okay? since we know, so F star, so therefore boundary of F star is homomorphism on sigma is 0, just that. Okay? The homomorphism under homomorphism 0 is mapped to 0. Okay? However, this is equal to F star sigma. F star sigma equal to boundary. That's the what I meant over there. So therefore, F star sigma is included ZQK prime. Okay? It's a one cycle. The similar thing will happen. Yeah, so therefore BQK is F star is included BQK. Okay? Okay. So since the sigma of boundary is either sigma is CQ plus 1, and this one is the BQ. This is BQ, right? And then F star of either can be written F star boundary of sigma, which is boundary of F star sigma. Okay? Therefore, F star sigma is inside the, so this is CQK and CQ plus 1 K prime. Okay? You understand? You understand? So what I did is just you start with let's call Q plus 1 and let's call Q Q plus 1. It's very simple thing. So BQ is just the image of this under this map. Okay? Image on the map and just bring it to here is the same as just bring first here and then just bring to image. Okay? So therefore it's the element, the image of this boundary map. So therefore it's inside of K prime. Okay. So therefore one can easily show that the this induced. So what we have done is the, I think it's better to write here. So what we have done is that so that induces homomorphism chain complex. Furthermore, it induces homology group of K and C coefficient to Q K prime and C coefficient homomorphism. Since we know that the so this one is DQ K divided by BQK. So therefore, if element included the Q cycle, that is mapped to Q cycle in the image. That's what it means here. Okay? Even if it's trivial as a homology group, it's mapped to trivial element in the image, okay, in a homology group. So therefore, this induces homomorphism between homology group. So any questions so far? Okay, so So then there's a theorem. So there's a theorem, but this is the very important to show the homotopy inverse homology group. So let's consider K and K prime are simplicial complex. So simplicial complex. And then you just consider the simplicial map. Simplicial map. So I is just some element. Did I write something? I is just write just a segment 0, 1 segment. Okay. So this can be understood. It's just that one simplex. It can be understood one simplex. Okay. And then this is simplicial map. Then we just restrict. So what I'm considering is something like this is a K here, and then we just consider the following things. We just consider the just cake, whatever, times I to the some whatever simplex. And let's consider something like that. Simplicial map. So this is K prime. Okay. So then you just restrict. So this is capital F, and you just restrict yourself that the let's consider F1, F0 is just map. So just restrict yourself in downstairs bottom. Okay. Bottom to here is F0. And top, restrict yourself in top and bottom, cause F1. Okay. So anyway, so I just restrict myself that the F0, you just restrict yourself F is K times 0, and F1 is capital F. It's just on the top and bottom. So this is 0 to 1. The segment is 0 to 1. Then the induced homomorphism between homology group of K and Z is so here you have a K. Okay. So every slice you have a K. Okay. Each slice you have a K. So this map K goes to K prime. This is simplicial map. This map is K prime. K goes to K prime. Okay. Also simplicial map. This K goes to this one. F prime goes to this one. So F1 K goes to K prime from top and bottom, a different map. For instance, one can just construct a simplicial map in such a way that the top is mapped to this place, but bottom is mapped to this place. Okay, at the bottom. And in the middle, so I think what you can do is just collapse this, rectangle to these edges. Okay? This collapse this rectangle to these edges, and you get this simplicial map. Yeah. Can you see that? For instance, So you can collapse this rectangle here to here, to the edge. Okay. Then you can construct a simple shadow. Okay. So it's a distinct simple shadow map. However, you will get the same. Oh my goodness! So why you didn't tell me? The induced homomorphism is the same. I have written the proof. I mean, sketch of proof. Should I go through that or not? Maybe I will come back this proof later. I think within a certain minutes, I think. So the proof, I may come back. So proof is written in the, idea of proof is written. Proof. Idea of proof is written in the lecture notes. And I may come back, but at this moment I will skip due to the time constraint. Yeah, so let me move on. So you can read if you want, or I may come back. Otherwise you can just read by yourself. But this is important theorem for homotopy invariance. So I'm going to talk about the homotopy invariance soon. So therefore I may come back. In any case, I will state this theorem again. So let's do this and something. So to compute a homology group, some simple manifold is easy to compute, but not in general. It's not that straightforward. Homology group has important information on the manifold, but it's not that easy to compute. And one way to compute using so-called Meyer-B torus exact sequence. Okay, so lots of typo in the lecture note. So let's consider the following thing. So Meyer-B torus exact sequence. Torus exact sequence. So given a Z module, like a free module, free abelian group. So we consider the homomorphism Fi plus 1, and so on. So M can be understood as something like a bunch of copy of Z. M can be understood a bunch of copy of Z, or you just consider some quotient group, like whatever, 2, 3, and so on, in general. In general, something like this one. So ZP, you know ZP, right? Z is Z mod P times ZP, PZ. So therefore, this is the element is generated by 0 to P minus 1. Okay. And then everything, so this means the integer mod P. So you can do the multiplication and the addition. At least you can have, at this moment the addition is enough. And F is a homomorphism. And if image of Fi is included kernel of Fi for any I, if this is the case, the distance this one it is called exact sequence. Exact sequence. Okay. So for instance, so that's what we have. So what I meant is exactly the same thing. So if you consider M and then image is include, if it is image included some kernel, so all the situations are the same as the complex we considered. This, so this is image of Fi plus 1. I should write it not plus 1. Its image is included, and then this is the kernel. So the kernel, if any I, so this is called exact sequence. Exact sequence. And we will construct this exact sequence by using the following thing. I mean, maybe Peter's exact sequence, I mean, when I learned, I just do the homework, like exercise and so on. And after that, I never used it till recently. I didn't use recently. Recently, I used maybe Peter's sequence to compute some homology from homogeneous space. It's very fun, actually. So let's consider K is a simple shell complex. Simple shell complex, everything is simple shell complex, which can be written as the K1 and the K2. Both of everything are simple shell complex. All are simple shell complex. Yeah. So simple shell complex, and also if you consider K prime as an intersection, K2 also a simple shell complex. So this is, so therefore we consider the situation like K1, K2, and then this is K. Here is K prime, and the entire thing is K. That's what we consider. And we have the other inclusion map K prime is inclusion map K1 and inclusion map K2, and then inclusion map to K. So therefore, for instance, I call it this one is I and J, and I call it K and L. So this induce the map, I think, yeah. So this induce a map that the phi, so given the phi which is equal to HQ prime is mapped to HQ K1, everything the Z coefficient now, with the Z coefficient in such a way that the Z prime, so X prime is mapped to indecisible homomorphism I star X prime and minus J star X prime. So what I meant is I just take the element x prime here, which is mapped to j star x prime or the minus quotient, and then it's mapped to I star x prime. And I just consider so this diagonal combination. And then we can again construct some map to the psi, which is HQ K1 plus HQ K2 is mapped to HQ the homomorphism, which is mapped to X1. It's very simple map. It's mapped to A star X1 plus L star X. So it's homology group is a group. The element, the group Z coefficients. You can add the addition. Okay, you can add addition. You can have the addition. So what I did is just you just consider some other map. So then x1 and x2, and you just map under this map. You just consider k star x1 plus k l star x2. Okay, so that's the simple operation. And then so we define some map, delta, I call it delta. We define the map HQ K goes to HQ minus 1 K prime in such a way that the given element Z, which is S1 plus C1, C2, so this is complex in Q K1, and this is a complex in K2. Okay. So you just divide. So here you can have some whatever it's, so Z is something like let's call a schematic diagram. It's just schematic diagram. Schematic. It's very schematic. The complex schematic diagram. So let's call this is Z. And C1 is very schematic. So it's just an image. This is, I call it C2. And then I call this element is, for instance, you can just decompose this one element is C1. That's, I just decompose Z in terms of element in K1 and the element in K2. And then I just, so this is the Z. And then the map, this one, into the boundary C1, which is equal to minus boundary of C2. So remember that it's element in homology group. So therefore, we know this is equal to 0. Boundary of homology group is 0. Therefore, boundary of C1 plus C2 is equal to also 0. Okay? Therefore, this means that the boundary of C1 is as a homology element is equal to minus, you get this relation, okay? And boundary C1 lives in K1, okay? On the other hand, this is actually element in boundary C2, so that living is K2. Therefore, the bound they have to live in intersection K1 and K2. Okay? So boundary C1 lives in K1. On the other hand, boundary C2 lives in K2. So therefore, this element should live in K prime. It's an intersection. So I define like this way, delta. And then one can construct so one can construct exact sequence. So it's going to huge exact sequence. So let's go. Let's start with 0, h, n, k prime. H and K1 plus KH and K2, H and K, sorry. And so on. And in the middle we have this one. And until today, you get the H0. So here I use a map phi for here. And I use psi here and delta to decrease the degree of homology. So this is the code, this is called Meyer-Vittorus exact sequence. So what's this good for? What is good for? So this Meyer-Vittorus sequence will help us to compute the homology group. So this Meyer-Vittorus homology, so given the H K1, so if you know the information on K2 and also its intersection K prime, one can compute H star of K. So if you know the homology group of K1 and the homology of K2 and the intersection, you can construct homology group of entire space. So that's a good for Meyer-Vittorus exact sequence. And let's compute. So let's compute this Meyer-Vittorus exact. So let's compute the homology. So we know that this Sn, okay? This Sn can be decomposed into two disks. So the northern hemisphere. So northern hemisphere D N, and then so I call it this one is K1. And the southern hemisphere southern hemisphere Dn, which I call K2, and the intersection is indeed just against sphere. Intersection is K prime, which is Sn minus 1. Okay? And this one is equal to K. And we already know the homology group of Dn, K1, and then homology group of K2 is isomorphic to Z in Q and Q. Q is equal to 0, 0, otherwise. This is by Poincare lemma. By Poincare lemma. And then what we are going to compute is just iteratively. So if we know about we know the homology group of S1 already. We already know homology group of S1, and then we iteratively compute the homology group of N sphere. Okay. So therefore, suppose, so we know the homology group of S1 is equal to Z, sorry, let's go Q, maybe it's better to write in here. Homology group of S1 is isomorphic to Z when Q is equal to 0, 1, 0 otherwise. Okay. So let's apply this into let's apply this configuration into the main vector sequence. So then what we get is that so first we want to compute what is the HQ of S2. What is this one? So we use this one. So let's HQ H0 of S1 goes to H0 of K disk, yeah, maybe K1 plus H0 of K2 is mapped to H0 of S2. 0, and there's a boundary delta is coming from H1 of S2, and then H1 K2, H1 K1, and H0 S1, and I just want to consider H2 of S2, and so on. H2 of S2 is just an iteration S2, and I think it's sorry, this is H1. Sorry, I think we should K1, K2. Am I correct? And we know this one is equal to Z. Z. Okay? Coming from here. Okay? Coming from here, this is ZZ. Q equals 0. And also this is Z equals Z. Okay? And also, we know this is equal to Z, and this is 0, and this is 0, okay? Okay? And this is also 0, and this is 0, and this is 0, okay? And we know this is exact sequence. Exact means the image is included the boundary, the image is included kernel, next kernel. Okay. So here Z is mapped to 0. So everything mapped to 0. Okay? So therefore the image here has to be included to the kernel of this one. Okay, image of under this map is the included kernel of this map. Okay, and furthermore, the kernel of this map is included. Image of this map is included kernel of this map. So therefore, this means that 0 something we don't understand, and z and then 0. Okay. So that's the situation we have now. Okay. You understand? And it's homomorphism. It's a homomorphism. So therefore, it automatically tells you that this has to be identity map. This has to be Z and identity map. So if your identity and goes to 0, so therefore image include kernel. So therefore this has to be Z. It has to be Z. Okay. The another information we have is that the H0 of manifold is D plus D by a connected component. Number is connected component. So another information we have is that this is the information. So the H0 of the manifold, given a manifold, and so if there's a connected component, one can always you can do the triangulation. Whatever triangulation, one can do that. Whatever triangulation one can do, but the point here. So any point of point is equal to 0. Okay. So therefore, it's a 0 cycle. However, any point in connected component is connected by one cycle. So this point and this point are connected one cycle. And if you take the boundary of this one cycle, you get this point minus this point. Okay. Therefore, as a homology group, they identify any point that are connected by one the line are the equivalent under the homology group. However, if you have another component, okay, and if you have a point here, this point cannot be connected to this one because they are different connected components. Okay. So therefore, you have a bunch of copy of Z depending on how many connected components you have. And since S2, how many connected components do you have? S2. 1. Therefore, this has to be Z. Okay? So, since this is exact sequence and Z everything maps to 0, so therefore this has to be onto, so it has to be surjective. So therefore, one of the component is mapped to S2. So in other words, in fact, So as you can easily see, given a K1 and a K2, okay? Given a K1 and K2, and then, so what I'm doing is that, so here. So given a point, and given a point here, okay? So you can always, so this Z and this Z are generated by point in northern hemisphere and point in southern hemisphere, okay? But however, under this map is actually indeed connected. There is some connected one cycle you can consider. Therefore, you can identify, okay? Therefore, Z mod Z is identified under this map, okay? And however, there is a, I would say, this boundary. So the intersection is S1, and there's a point here. There's a point here. Point here. And this is indeed inclusion. So as we know that this point pointing here is mapped to minus point identity minus point. Okay. So minus point. So this point here is included inside Z plus C. Okay. Z plus C. And then under the map from here, you can just add them up together, so you get 0. So therefore, you have at the end of the day, so you have Z plus C, and Z go to 0. Some element A is mapped to A plus minus A inverse. That's the map. And you have A and B. You map to A plus B. So that's a map you will have. So this is the injective, this is surjective. And this means that and also here you have started with 0. So therefore there's only canonical choice you can have in the middle. So you has to be 0 in order to have the exact sequence. So therefore the H2 S2 of the homology group Q is equal to Z when Q equal to 0 or 2 and 0 otherwise. And the same situation will happen, everything in the middle, if you increase distance to n. If you change to n, everything in the middle becomes 0. But the only thing that is relevant is indeed n minus 1. And then this becomes n minus 1, and this becomes n, and this guy is n, and n, and n, and n, and everything in middle is a trivial, and the H0 stays the same. Okay? So therefore, this becomes Q equal to. That you can show by using the difference sequence. So let's see how you compute homology group of sphere. So that's intuitively clear that so essentially this whole sphere, if you take, there's no boundary, okay, whole sphere. So the whole sphere, if you apply the whole sphere to the end, this is 0, there's no boundary, okay? That's the element in top form, in the n, Q equal to n, okay? And then in the middle, there is no homology because everything is a boundary or something. So for instance, Sn minus 1 is a boundary of the northern hemisphere. So therefore, in the middle, there is no homology class. And the H0, there is a one connected component, so therefore, zero's homology is isomorphic to 0. That's how we compute the homology. So let's finish here. Today. That's it for today. If you have questions, just tell me.